Hi students, so this is session 2 of module 4. So in this session, I'll be discussing about one of the important dimensionality reduction technique which is known as principal component analysis or PCA. What are the different concepts inside it, and we'll see different terms like eigenvalues and variance and what is the relevance of it in PCA. So principal component analysis is one of the important dimensionality reduction technique. It is a powerful statistical procedure that takes a set of observations of possibly correlated variables and uses an orthogonal transformation to convert them into a set of values of linearly uncorrelated variables. So that uncorrelated variables are known as principal components. And the key idea is that these new principal components are linear combinations of the original variables. They are also orthogonal or perpendicular to each other. And the first principal component is the most important one. It accounts for most of the possible variations of the original data. So crucially, the number of principal components we end up with is less than or equal to the smaller of the number of original variables or the number of observations. So here you can see some visualizations. You can visualize the problem PCA is solving. On the top graph, you see our original data, which is plotted in 2 dimensions, X and Y. Notice how the data points are scattered over here. And the bottom 2 graphs, these shows the total variance along the 2 original axes. The horizontal axis X, it has a certain spread of data, and the vertical axis Y, it has a certain spread. So our goal is to find new axis that capture the total spread or variance most efficiently. So if we project this data onto the x-axis, we lose a lot of vertical informations, and if we project it onto the y-axis, we lose the horizontal informations. So here is actually the power of PCA is revealed. So in this diagram, we are looking at the same data, but now we have introduced the first principal component or PC1 represented by the long arrow. So PC1 is the direction in the data that captures maximum variance. So this line passes through the center of the data, which is the mean of x and y coordinates shown by this solid dot. So if we project all our data points onto this single line, we retain the maximum amount of information possible, even though we have reduced the dimensionality from 2 axes to 1. Now this diagram shows the first and second principal components PC1 and PC2. So PC1 is again the axis of the largest variance and PC2 is the axis of the second largest variance. So you can notice how PC2 is perfectly orthogonal or perpendicular to PC1. So this is a fundamental requirement of PCA. Every principal component must be orthogonal to all other principal components, and this ensures that the components are linearly uncorrelated and there is no redundant information between them. So these two component system acts as a new coordinate system for our data, which is now aligned with the data's maximum spread. Now let us look at the computational process, that is the PCA algorithm. So this is a step-by-step procedure to find out those new principal components. So step 1 is get the data, that is our starting point, and step 2 we will compute the mean vector new. So this finds the center of the data, which is the origin for our new component axis. And in step 3, we have to calculate the covariance matrix, and this matrix tells us how much the variables change together, capturing the correlations in the data. And in step 4, calculate the eigenvectors and eigenvalues of the covariance matrix. So the eigenvectors are our principal components and eigenvalues tells us the magnitude of variance explained by each corresponding component. And in step 5, choosing components and forming a feature vector. So we sort the components by their eigenvalues and select the top k components that capture most of the variance. So we then combine these chosen components into a feature vector. And finally, step 6, deriving the new data set. So finally, we use the feature vector to transform our original data, projecting it onto the new lower dimensional space defined by our chosen principal components. Now let us formally begin the PCA algorithm with step 1, that is data. So we start with our original data set. So this table shows our data where we are having n features or variables. There are n features or variables denoted by x1 through xn. We have capital N examples or observations in our data set, and the values are arranged in this table where xin, it represents the value of ith feature for the nth example. So this matrix is what we will work on throughout the process. Next we move to the core statistical calculations. Step 2 is compute the means of the variables. For each variable xi, we calculate its mean denoted by xi bar. This is simply the average of all the n examples for that particular feature. So that formula is given over here. And step 3, we have to calculate the covariance matrix S, capital S. So this is an n by n matrix where the element in the ith row and jth column, it is the covariance between the variables xi and xj. And the covariance is calculated using this formula, covariance of xi and xj. That value will be filled in this table. So the covariance matrix is essential because it captures how all our variables relates to each other. Once we have the mean and the covariance matrix, we have the statistical foundation that is needed to find the principal components. And next step is to calculate eigenvalues and eigenvectors. So this is a key mathematical step. We have to calculate the eigenvalues and eigenvectors of the covariance matrix. So the eigenvectors are the actual principal components and the eigenvalues tells us how much variance each components capture. So we set up a polynomial equation using the covariance matrix S and the identity matrix I. So determinant of S minus lambda I is equal to 0, and the roots of this equation, that is lambda 1, lambda 2, etc., lambda n, they are the eigenvalues. Now if lambda is an eigenvalue, the corresponding eigenvector is u, capital U. It is found out by solving a system of linear equations. This eigenvector will gives us the direction of the principal component, and this process gives us n pairs of eigenvectors and eigenvalues with the eigenvalues representing the variance captured by their corresponding eigenvector. Now as a sub-step, it is critical to normalize the eigenvectors. So a normalized vector has a length or norm equal to 1. So the norm of a vector x is defined as the square root of sum of the squares of its elements, that is given over here. So we compute the normalized eigenvector ei by dividing the original eigenvector ui by its norm. So these normalized eigenvectors E1 through En will be used in the next step to transform the data. Now in step 5 we have to derive the new data set. So we order our results and performs the final transformation here. First we have to order the eigenvalues from highest to lowest. The unit eigenvector corresponding to the largest eigenvalue lambda 1, that is our first principal component E1. and the one corresponding to lambda 2 is the second principal component, and so on. So we choose a number of components P where P is less than or equal to n, the original number of features. Then we choose the P eigenvectors corresponding to the largest eigenvalues E1 through EP and form a P by N matrix called the feature vector capital F. And this feature vector capital F is the matrix we use to compress our data. Now finally we reach step 6. Step 6 in the sense this is new data set itself. So to get our new reduced dimension data set X new, we have to multiply the feature vector F by our original centered data matrix X, and the centered data matrix X is simply our original data with the mean of each feature subtracted. So X new is equal to Fx. So the matrix X new is equal to the matrix X new is a P by N matrix. This gives us a new data set with N samples but only P features, where P is much smaller than the original N. Now the conclusion, this is how this principal component analysis achieves dimensionality reduction. So it is important to note that it is not possible to get back the original n-dimensional data set from the new data set because we lost some variance when we discarded the components with the smaller eigenvalues. So however, the P components we kept contains the most crucial informations for analysis. Now let us look at an example of how to apply this PCA algorithm. So you will be getting questions from PCA like this, to a problem like this. You have to apply PCA and find out the principal components for the given data set. So this problem also asks us to use PCA to reduce the dimensions from 2 to 1 for the data which is shown in the table. So our data set is having two features x1 and x2, and there are 4 examples. So we have to follow the steps we previously seen, starting with the mean and covariance. So our first step is to calculate the means of the variables. So for x1, the mean x1 bar, that is the average of the 4 values that we have seen in that table. 4 plus 8 plus 13 plus 7 by 4, we got 8. And for x2, the mean is x2 bar. So that is 11 plus 4 plus 5 plus 14 by 4, which is 8.5. And the graph on this slide here, it is a scatter plot of our original data points, and the point x1 bar comma x2 bar, or 8 comma 8.5, that marks the center of our data. So this center point will be the origin of our new principal component coordinate system. Next is the calculation of the covariance matrix. So the covariance matrix S, for a 2D problem, it will be a 2 by 2 matrix. We have to calculate 3 unique covariances: the variance of x1, the variance of x2, and the covariance between x1 and x2. So variance of x1 is x1 comma x1, and that will get us 14, and x2 comma x2, that is 23, and covariance between x1 and x2, that calculates to minus 11. So since the covariance matrix is symmetric, covariance of x2 x1 will also be minus 11. So after calculating all these values, we get the covariance matrix like this. S is 14, minus 11, minus 11 and 23. Next, we have to calculate the eigenvalues of the covariance matrix. So to find the eigenvalues, the formula is determinant of S minus lambda I is 0, where I is the identity matrix. So we substitute that covariance matrix S and the identity matrix I to get the determinant equation. And after that, this is simple maths. We have to solve this determinant equation. This is a quadratic equation. So you can solve it and get the values of lambda. So lambda 1 is 30.38 and lambda 2 is 6.61. So since lambda 1 is larger, the eigenvector corresponding to lambda 1 will be our first principal component, and that will capture the most variance, which is what we need to reduce the dimension to 1. Next is the computation of the eigenvectors corresponding to our largest eigenvalue lambda 1. So we have to use this equation S minus lambda 1 I x, that is equal to 0. So u1 comma u2, that will be our eigenvectors. So that is just, we are just substituting the values and getting the eigenvectors. Again we'll get two equations, we have to solve it and get the values of u1 and u2, that will be our eigenvectors. And then to use this component for transformation, again we have to normalize it according to our algorithm. So we first compute the length of the norm. So this is the equation for that, and then that normalized one is 19.73. This is the eigenvector. And finally the unit eigenvector, that is obtained by dividing the components of u1 by its own norm. In that we got e1 as 0.5574 and minus 8303, and e2 as 0.8303 and 0.5574. Next we have to plot this. So I have already told that this, we have marked the center of the data and the principal components has to pass through this centric point. So how to correctly draw this E1 and E2 is that first mark the center x1 bar and x2 bar. Then first we have to draw E1. So already we got the values for E1 as 0.5574 and minus 8303. So that vector tells us to move 0.5574 units in the positive x1 direction and minus 8303 units in the x2 direction from the center. So we can draw a line through that particular point, and we have to draw the line that aligns with the longest most spread out part of the data. And next is we need to define E2. So the line for E2, the eigenvector E2 is 0.8303 and 0.5574. So that line must be mathematically perpendicular to E1. So just mark those points and we need to draw these lines passing through that points of E1 and E2. Now next is to complete our task of reducing the dimension to 1. We must calculate the projection for all 4 of our examples. So as we saw, the formula for the new one-dimensional value pk for any example k is pk is 0.5574 into x1k minus x1 bar minus 0.8303 x2k minus 8.5. So by applying this formula to all the 4 data points in our original table, we'll get the following values. For first example, that is 4,11, we get it as minus 4.30. And for second one, same equation follow. We get these many values. So with that, we can write down all the first principal components over here. So the crucial final step in PCA is to determine how much informations we actually kept. So we do this by calculating the percentage of variance explained by our chosen component E1, and the total variance in our original 2D data is the sum of the two eigenvalues, that is lambda 1 plus lambda 2. So total variance is just sum up the values of lambda 1 and lambda 2. Here it will be 37, and the variance explained by our first principal component E1 is simply its eigenvalue, that is lambda 1, which is 30.38. That was the value we got. So the percentage of total variance explained will be lambda 1 by lambda 1 plus lambda 2. By solving that, we get a value of 82.12 percentage. This means that by reducing the data from 2 dimensions to 1, we managed to retain over 82% of the original variability in our data set. So this demonstrates the efficiency of PCA, and in conclusion we can say that PCA allowed us to compress the data while retaining the vast majority of its informations, making it excellent for visualization or as a pre-processing step for other machine learning models. So here just I have plotted all these given data points to this new principal components, and you can see how much variance is there over here. So that is the geometrical representation of one-dimensional approximation to the data. So that's all about PCA. Thank you.